Hello everybody, this is Mr. Gaska, my little intro, I guess. And today we're going to be going over Unit 3's multiple choice question set B, which is in Unit 3 we talk about centripetal force and circular motion. Uniform circular motion means a constant speed around the circular path, and the radius generally does not change. So here's going to be our first question. Again, you are encouraged to follow along on AP Classroom since it'll make it a little easier to see the formatting of these questions. As I think these here are going to be a little zoomed out. I can always zoom in if you guys would like while we're looking at the answer choices and reading the question. But it can be a little hard for us to see the whole thing. Okay, so a horizontal circular track a circular track for running has 4 lanes as shown in the figure. Various runners of different masses use the track. In each case, the center of mass of a runner follows a circular path around one of the lanes, around the track in one of the lanes. So for instance, maybe, oh no, my tablet turned off. Too much inactivity. Where's my mouse? Give me 1 second. And we are connected, right? Yeah, we are connected. Oh, wait, I have the wrong USB connected. I was charging my mouse this time, so that's why it's not working. I have Bluetooth, but the Bluetooth got janky last time, so I figured, you know what, let's just be wired. Okay, so let's go ahead and see here what we're thinking. So Johnny can go in this circular path. Jenny can go in this circular path. Billy can go in this circular path, and Bobby can go in that circular path, so to speak. That's kind of what they're telling us here. And they say, consider a runner in lane 1 with a speed v1 and a runner in lane 2 with a speed v4, where the ratio of the speeds v4 over v1 is equal to 2. The radius of lane 4, is b times the radius of lane 1. So we could say v4 is b times, not b, r, the radius of 1. Both runners have the same mass, and the question is, which of the following claims is correct about the net forces F1 and F4 exerted on the runners in the lanes respectively? So we'll go ahead and do a 30-second poll here. We'll see. Oops, not that one. That's a 3 choices. Here we go. And I believe I am recording. Yeah, okay. Okay. So let's go ahead and take a look at this one here. So they're asking about a statement involving the net force on runner 1 and runner 4. So in either case, these are net forces and we're moving around in a circular path. So what we have been told, or really what is the case, is that the net force that causes us to move around in a circle is called the centripetal force. So this is really asking about how does the centripetal force on runner 1 compare to the centripetal force on runner 2. So we are going to try to remember, well, what do we know about centripetal force? Well, the centripetal force is really the net force when we move around in a circle. And so the net force, according to Newton's second law, is m times a. And what we have learned is that if we move around in a circle, the acceleration is really something called the centripetal acceleration, which can be calculated by v squared over r. So usually we say that the net force when we move around in a circle is called the centripetal force and is calculated by mv squared over r. All of this right here is the centripetal force. In our last video, we talked about how it's a tidal for the net force. When we dub the centripetal force when this causes us to move around in a circle. So let's go ahead and look at some of these ratios. So they basically want us to say F4 is some ratio of F1. So let's go ahead and do a ratio of the net force on 4 over the net force on runner 1. Well, the net force on runner 1 is going to be the net force on runner 4, which they're calling F here, is going to be the mass of runner 4 times the velocity of runner 4, quantity squared, divided by the radius of runner 4. And we're going to substitute those in here in a second. The net force on runner 1 is going to be the mass of runner 1 times the velocity of runner 1 squared, all over the radius for the path of runner 1. Now we can go ahead and make some substitutions because we've been told about them. For instance, we know that both runners have the same mass. So when we do this comparison or this ratio, this part doesn't really matter. M1 equals M4. And then on top of that, we were told that the ratio of V1 or V4 over V1 is 2. So let's go ahead and say V4 is really 2 times V1, and we're going to substitute that in here. And so we start to get this expression, and I'm going to actually move this guy over because it's in the way. And we're going to get 2 times V1, and we need to square that monster. And then they tell us that the radius of lane 4 is B times the radius of lane 1. So I'm going to go ahead and put that in here for this guy. B times R1. And all of this information pertains to runner 4. All we did is we made a comparison and we substituted so that everything is in terms of V1 and R1. And then for this guy, that becomes V1 squared divided by R1. So what do we get out of all this? And I'm going to actually make my division sign here a little bit smaller. And you know what? Let me write this a little bit more properly. Okay. Well, this can clean up a little bit. We get 2 squared is 4 V1 squared over B times R1. I'm going to write it like a fraction here because I'm running out of space. And then all over V1 squared all over R1. And so hopefully we recognize that some of these quantities are going to cancel. I'm dividing by V1 squared and I'm dividing by R1. And so what we get out of all this, and I'm going to go ahead and also erase this to make some room, space created. And what all of this becomes is that the ratio of F4 to F1 is 4 over B. Everything else canceled out. And so this tells us that force 4 is equivalent to 4 over B times F1. And so B is our answer here. And this is the mathematical proof. The way I would think about it is, okay, well, it's 2 times bigger and it's in the numerator, so I'm going to get a factor of 4 on the top. The radius is B times bigger, so I'm just going to put the B on the bottom. And there's my ratio. That's like the quick way, I think, to think about it. Recognizing that the centripetal force here is the net force, and we can use V squared over R to our advantage. And so we do 2 squared on the top, that's 4, and then R on the bottom is B, 4 over B. Let me know if we have questions over this. I'll go ahead and scroll to the next one so we can go ahead and take a look at it. So in the next question, we are told, consider a runner in any of the lanes moving at a known tangential speed. Which of the following measuring tools, if any, could be used to experimentally determine the centripetal acceleration on the runner? Okay. We'll go ahead and call it there and let's see. So we have learned that the centripetal acceleration is given by v squared over r. And we already know this quantity. It is known as a tellus. So really we just need the radius, and we're going to get that radius by a meter stick. Very good. If we were thinking a protractor, let me know what we were thinking there, because I guess my intuition would be like, well, yeah, they're changing path along here, and then maybe we could get the angle, and if we know the angle, we might be able to get that distance using like r times theta or something. But the thing is, you still need a meter stick to know either this length, the arc length, and so the protractor won't give you enough to get the radius of the path. If you guys look at another formula for the centripetal acceleration, if we remember, we've said that v is r omega. So v squared is r squared omega. And so another way to write the centripetal acceleration is r squared omega squared, all over r, and that guy cancels. And another way to get the centripetal acceleration is r omega squared. So maybe we could use a protractor to get delta theta, the change in angular position, over the change in time, but we would need a stopwatch, and we would still need the protractor, the meter stick. Okay, so I don't think the protractor alone will do it for us. Let's go to question number 3. So in question number 3, they say, now consider 4 runners running around the track with the same tangential speed, with 1 runner in each lane of the track. A student is considering using the following equations to determine which runner has the greatest acceleration. Which equation should the student use and why? Alrighty. So if we look at this, we have to be very careful. This here would be our tangential acceleration. This would be the acceleration along the direction we are moving. So if we're moving around acceleration, if we're moving around a circular path with constant speed, what this tells us is that our acceleration in the sideways direction is 0. Okay. The reason why we experience an acceleration when we go around in a circle is because our velocity changes direction. The speed stays the same amount of fastness at this point, and I don't think blue is a very good color here. So here I have a certain speed in each of these instances, but because the direction changes, we have an acceleration towards the center. And when your acceleration is perpendicular to your velocity, it doesn't point forward to get you to go faster. It doesn't point backwards to slow you down. It only acts sideways to turn. So very important. We are looking for the centripetal acceleration in this. Now, let's say we released a rabid tiger or something, and we have Johnny over here, and the tiger's like, I'm going to eat you or whatever. Well, then he's going to start to speed up and run faster along the path, and then this equation would be handy. But while they're running all at the same speed, this equation is useless. So D is our best answer choice. And again, let me know if we have any questions. Okay. The next question is a little difficult to show all at once, so we're going to have to rely on AP Classroom to help us out here. And I don't know where my scroll bar went. Okay, so we're going to be looking at a region X in some kind of roundabout situation or highway interchange. So they say, where are my, it's kind of hard to see my, okay. So a truck in a traffic circle travels in a circular path at constant speed v naught, or v original, while passing through region X of the circle as shown in figure 1 above. A diagram representing the forces exerted on the truck in region X is shown in figure 2. So that's this guy here. So when the truck is at this point in region X, this is the bird's eye view, but this is the side view. If we notice, they give us the normal force and the gravitational force, and the friction is acting to the right. I'm sorry, to the left. At a later time, a car with less mass than the truck passes through region X at the same speed and the same distance from the center of the circular path. Where's my cursor? I kind of don't like this. It's kind of hidden. There we go. Give me 1 second. Can I use my arrows? Wow, this is actually really tedious. I'm really sorry. I can't seem to get this to move back to the, there we go, okay. Same traffic circle as the truck. The coefficient of friction between the car's tire and the ground is the same as that for the truck's tires and the ground. Which of the following diagrams could represent the forces exerted on the car in region X compared to the truck in region X? Assume the length of each arrow is proportional to the magnitude of the force represented by the arrow. So here they want us to choose the correct free body diagram in relation to the truck. When the truck was in that region, we had these forces acting on it with these lengths. And now they want us to choose for the car. Which of these forces will represent, or which of these free body diagrams would be equivalent to describing the forces acting on a car at that region? Relaunch poll. Okay, alrighty, so let's go ahead and see here. We are told that the car has less mass than the truck. So the force due to gravity of the car is going to be less than the force due to gravity on the truck. So in the first scenario for the truck, it was 2 squares of length. So we cannot have 2 squares of gravitational force, okay? Even though the forces are balanced, this is saying that the car has more mass, or has the same amount of mass, sorry, as the truck. It has more mass than what we would expect a car to have. So that one's not going to work out. Answer choice A is also out of the picture. This would imply that the car is accelerating upwards from the road, where the road would be kind of like this. So not the case. So then that leaves us with B or C, which show that the force due to gravity is less than before when we're considering the car. And the forces are balanced. So that looks good. Now we have to beg the question of, well, what about the frictional force? Well, we learned that the centripetal force is equal to, the centripetal acceleration is V squared over R, and the centripetal force, which is the net force, equals mv squared over R. So because the force depends on the mass, we're going to want to go with B, because the car here is going to need less friction to bring it around in the circular path because it has less mass. Even though it goes the same speed and the same distance from the center of the track, the accelerations are the same for both the car and the truck, but the mass of the car is less than the mass of the truck. And so C is our best answer choice. Let's go to question number 5. So a student swings a ball of mass m on the end of a string in a vertical circle of radius r, as shown in the figure above. Also shown is a diagram representing all of the forces exerted on the ball at the bottom of the circle, where its speed is v original or v naught. So something like this. What is the magnitude of the acceleration of the ball at the bottom of the circle? So let's see here, please. we'll go ahead and do a new poll. And it's a little hard to read, so let me try zooming in a little bit, and while keeping the free body diagram in view. And I'm going to assume those of you guys are working, those of you that are here are working on AP Classroom, so you should be able to see it. Okay, so that is time. 7 out of the 9 people got a chance to submit, and they all got the correct answer. If we look at this, traditionally we say towards the center is the positive direction of motion. And so here we're going to have to the center be positive. And so that's going to be the tension, which I think is Ft minus Fg for Newton's second law. And we set that equal to ma. And because we move around in a circle, this is the centripetal force right here, equals m times a. And they want the acceleration, so we just divide it by the mass. Very good. Let's go on to the next one. Question 6. There we go. The figure above shows 2 identical asteroids that are located near each other but are not in contact. Various locations are labeled on the asteroids. If an astronaut wants to stand on one of the asteroids and experience the largest net gravitational force, where should the astronaut stand? Okie dokie. We'll go ahead and call it here. And so this one can seem a little difficult to analyze, because it's like, well, shoot, how do we go about it? So if I am here at point C, let's say I have my astronaut here. Well, it's going to feel a gravitational force from this guy. And that gravitational force will definitely be larger than the gravitational force from asteroid 2. 1, 2. So because these guys point in opposite directions, these are going to cancel themselves out. So C is probably going to be where the gravitational force is the weakest, because one guy is pulling me away from the other asteroid, and I'm going to feel slightly less heavy, or significantly less heavy, actually. When I'm at point D and point B, those are pretty much the same thing. Whether I stand on the top or the bottom, that doesn't change anything. Now, if we look at this scenario here, and I'm going to go ahead and clean this up, or actually, let me do it off to the side. If I draw the free body diagram for the astronaut at D, we have a gravitational force from asteroid 1 pulling us this way. And then we have a gravitational force from asteroid 2, essentially pulling us to the side. It's actually kind of at an angle, because it's going to the force due to gravity is going to align our centers of mass. So the force due to gravity is going to be directed along a line between our centers of mass. So our force due to gravity is going to be something like this. If we look at location B, well, I'm going to have the force due to gravity from asteroid 2, something like this. And the force due to gravity for asteroid 1, something like this. And so here, these guys, because of their vector addition, we can kind of put them together and we kind of get a resultant force, something like this. The sum of these two vectors. Now, if we look at A, if I'm at location A, I have the force due to gravity from asteroid 1, as well as the force due to gravity from asteroid 2. And if I'm here, I'm going to be pulled towards the center this way by that guy, and I'm going to be pulled towards the center by that guy. And these two point in the same direction. So B and D are going to give us slightly more gravitational force, but not as much as A, because here we have all of our mass to our right pulling us to the right, as opposed to some of that mass pulling us down and to the side. Let me check the chat just in case. Okay, we'll go ahead and continue. Question 7. A little bit more. So here we have some kind of mass when moving around in a circle of radius r, and it looks to me like this string is providing some kind of tension that is going to pull on a force sensor for us to measure that force. So it reads, a student conducts 3 experiments to determine how certain quantities influence the centripetal force responsible for an object to spin in a horizontal circle. The student uses one end of a string to attach the object while the other end is connected to a force sensor that allows the student to change the tension on the string as shown in the figure. Student, hold on, let me minimize my taskbar maybe, or let's move it to the right. Maybe that'll give me my, okay, this is gonna be, I don't know why all of a sudden my taskbar is not or my scroll bar is not showing up on the window. It's hidden sometimes. Okay, so the student uses one end of a string to attach the object while the other end is connected to a force sensor that allows the student to change the tension in the string as shown in the figure. The student records data from the 3 experiments in the table above. Which of the following experiments, if any, collected data that do not agree with the expression for the net centripetal force on the object? Okay. We have about 2 submissions. I'll go ahead and give you guys a little bit more time. Yeah, this one maybe requires us to process the numbers a bit more. All right, okay, we got about 5 out of 9. We'll go ahead and call it here. I think that's good enough. And if you were working on it, continue working on it. So the centripetal force, which is the net force, is going to be mv squared over r. And in any good experiment, you only want to change one thing at a time. So let's see here. When I have a mass, I have a force of 4 newtons. If I double the mass, well, I have twice the force. Okay, that's consistent. The force is proportional to the mass. And so we're seeing that so far. If I triple the mass from the original amount, I'm going to triple the force from the original amount. And so this one checks out. At the same time, if we vary the radius while keeping the mass and speed constant, the centripetal force will be inversely proportional to r. So if I cut r in half, then the force is going to get cut by 1 over a half, which really means it's going to double. So if this guy goes down by 2, this guy's going to go up by 2 because they're inversely proportional. And if I cut it into a third of its original value, the force will be 3 times as much. And so this one also checks out. The last one here, if I go from this speed here, from 2 to 4, that's a factor of 2 times the speed. But when I keep the mass and the radius constant, the centripetal force is proportional to v squared. So if I double the speed here, I'm going to need to quadruple the force. So going from 4 to 16 is definitely 4 times that amount. This one may look a little bit weird because like, well, what do we do here? Well, the ratio here is 3 over 2, 1.5. 1.5 squared is, I believe, 2.25. So if we take this value and we do 9/4, plot twist, I'm going to get something wrong. Let's see here. Oh, dude, well, think of it this way. We'll just square, that's 9/4. So that works out. Yeah, because we needed to do it by the square of that. So 9/4 divide, yeah, 2.25. Okay, so there's our answer. All the data are as expected. So nothing wonky here. We just had to kind of look at relations. Okie dokie, let's go to the next one. Planet X, planet Y, planet Z. At one point in their individual orbits, 3 planets, X, Y, and Z, are all along the same horizontal line. The gravitational force on planet X from planet Z is going to be F0. The distance from the center, please come up. So the distance from the center of mass of each planet to an adjacent mass is given in terms of R original, and the respective masses are given in terms of M original as shown above. What is the net force on planet Y, and what reasoning supports this claim? Fumbling here with the poll, relaunch poll. And this was going to take a while to work out. So go ahead and work it out, and I'm going to get started on it. So you guys are real fast. Okay. Oops, I'm sorry. I just saw the chat. 36M for the. Yes, sir. Yes, sir. It is. Thank you. I do appreciate that. Are C and D saying that Y is applying a force on itself? Ooh, I haven't checked that. I'll check it right now in a second. Okay. So what is the thought process for this one here? And let me know if I made any other mistakes in my calculations. So the first thing is they tell us that the gravitational force on planet X is written as FO. So when we go ahead and do Newton's law of gravitation, we've learned that that's some big constant, mass 1 times mass 2, all over the distance between them squared. And so in a 3-body problem, we have to do 2 calculations. There's a gravitational force between these two of some magnitude, which I'm calling Fx. And then there's a gravitational force between these two, which I'm calling Fz. So when we did the force from planet Z on planet X, and there's like a third force over here between them, but we're not going to worry about drawing that, okay? Because this question is asking about planet Y, so I'm only concerned with those. So what we want to do first is find out, well, how much gravitational force is this right here? Well, the mass in the system planet X and planet Z is going to be, well, 9MO for this guy. That's M1, usually the bigger mass is what I do, times MO, and that's just going to give me 9MO squared on the top part. Then we ask ourselves, well, how far apart is planet X from planet Z? And so it's going to be a total of 3 radii away. So when we square that, that becomes 9RO squared. And so what we find out is that FO is really just MO squared over RO squared. Now we can go ahead and start doing a free body diagram for planet Y. Well, planet Y is going to be attracted gravitationally to both of these planets. So let's find out the magnitude of each of these forces. The gravitational force between planet X and planet Y is going to be 4m times m, that's m1 and m2, and the distance between them is RO squared. So we can go ahead and multiply this through, clean it out, and what we find out is that the force from X on Y is given as 4MO squared over RO squared. And we do the same thing between planet Y and planet Z, except planet Z has 9 times MO, so that's the mass of planet Z. And then we're going to multiply that by 4MO. Now, I don't know how to multiply 9 and 4, but someone told me that it's equal to 36. So thank you, because I put 32 originally. And then, well, the distance between them is now 2RO, and we need to square that bad boy. So when we do all this, we get 9 times 4 for this guy is going to be 36 on the top, MO squared, over 4RO squared. 36 over 4 is 9. So we have 4, just kind of putting things in terms of FO, 4FO this way, and we have 9FO this way, for a total of 5FO in this direction. And so I think C is going to be your best answer choice. And so we could kind of have taken, what do you call it? A guess that it was going to be between these two. Even though the distance usually makes a bigger impact because it gets squared compared to the mass, here, the total gravitating mass is essentially 36, 4 and 9. Before it was just 9. And so we have like 36 times more mass, sorry, 4 times more mass in this scenario, or 36 times more mass compared to 9 is 4, yeah, 4 times more mass involved gravitationally. And so we could say, okay, well, that's going to offset this distance, and it's going to have a more noticeable effect to the right. And so the gravitational force from planet, hold on, let me make sure I read this question here. What is the net force on planet Y? Because the gravitational force from planet Y is greater than the gravitational force from planet X. I think here they meant Z. I think there's an error here. Anyone care to enlighten me? FO to the left because the gravitational force is greater. I don't think so. That's 4 versus 9. No. Yeah, I think they fumbled here. I'm going to say that C is our best answer choice. Let me check with the powers that be. Yeah, they say C is correct. Yeah, they say planet Z, but then they write Y in the answer choice. But in their explanation, just in case, let me go ahead and put that here. It's the exact same work we did, but just in case, here's the explanation for that bad boy. Okay, let's go on to question number 9. A planet orbits a star in a path as shown in the figure. The planet's mass is much smaller than the star's mass. Which two of the following claims are correct about the accelerations associated with the planet, star, and planet-star system? Select 2 answer choices. Select 2 answers and justify your selection. Whoops, let me end the polling. This is going to be a multiple correct. So let's go. Alrighty, I think we're starting to learn our physics. But then again, the people that show up are usually the ballers, so there's a sampling bias there. All right, we'll go ahead and call it here. I just saw the time and I am moving even slower than usual. So they're each going to feel the gravitational force due to each other. So like if we wanted to calculate the force due to gravity, the force due to gravity on one of these guys is big G, the mass of the sun times the mass or mass of the star, mass of the planet over the distance between them squared. So if we found out that this force due to gravity was, I don't know, 10 newtons, what this means is that the planet feels 10 newtons this way and the star feels 10 newtons this way. Last time in our calculations, and I just made up the number 10, just in case anyone's wondering, like, where did you get that number? Made up. So really important. Let's say you jump off of a tree, right? You're just jumping. You're not jumping off a building or something. So in this instance, you're falling towards the earth and you feel a gravitational force pulling you towards the earth. And the earth is also feeling this force accelerating also towards you. So when you fall towards the earth and the earth also falls to you. The big issue though is the acceleration of the star is going to be much less, or the acceleration of the earth is going to be much less as you fall because it's that much more massive. So very important, both the planet and the star accelerate because they exert, each object exerts a force on the other. So it's the same magnitude, but the mass of the sun is way, 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 way bigger than the mass of the planet in this case. And if we look, acceleration is force, net force divided by mass. And so when this is really huge, that's going to get really small. So there's one. Now, the other part is the center of mass statements. So because these two forces are internal to this system, the system is a planet and star. As far as we know, there's nothing else interacting with these bad boys. When these guys act on each other with this force, Newton's third law says, you're an action-reaction pair. Your forces are going to be equal and opposite. So they're going to cancel out, and there is no net force on the system. Individually, each of these objects have a net force, but as a system, that force between them is internal, and there is no external force. No net external force. Oops. So there's our answer choice. Very good. We have the Earth and some satellites. A satellite moves in a circular orbit at a constant speed v0 around Earth at a distance r from its center. The force exerted on the satellite is Fo. An identical satellite orbits Earth at a distance 3r from the center. How does the tangential speed v of the satellite at distance r compare to the speed of the satellite at 3r? Free lunch poll. Yeah, this one's a little weird. It's like, what do we do? Okay, so this one's going to take a little longer to explain. So if you guys remember, and I'll give you guys a short one real quick. If you guys remember when we were doing our orbital motion unit, we found out that we can get an expression for the orbital speed. And what we found out is that it is given by square root of g, the mass that we are orbiting. So in this case, that would be the mass of the Earth all over the radius. So the takeaway is orbital velocity is an inverse square root relationship. V is proportional to 1 over square root of r. So if we look at this, the radius now is 3 times bigger. So what we find out is that the tangential velocity for satellite, for this guy here, is going to be 1 over square root of 3, the original velocity here. This guy's going at some v original Here they're calling this guy B tangential. And so D is our best answer choice. Now, how the heck do we get this? Because this is not included in the AP equation sheet. This is sadly kind of like things that you should memorize. And I don't believe in memorization, but I think deriving it can take a little long. For instance, if we look at the centripetal acceleration, well, that's V squared over R. And then the centripetal acceleration is really going to be the acceleration due to gravity, which is given by big G, the mass of the Earth, all over R squared. And so we get V squared over R equals big G, mass of the Earth, all over R squared. We move over the R's and we move over this R. It cancels the power on that, and we get V is the square root of Gm over R. All I did was square root afterwards and canceled that guy out. If you're wondering, well, what happened to the mass? Well, the force due to gravity is going to be the mass of the Earth times the mass of the satellite all over their distance squared. And then the centripetal acceleration is going to, or the centripetal force is going to be mv squared over R. But this mass is always the one that is accelerating, the one moving around. And well, in reality, in higher level physics, you need to include the mass of the Earth in this case for the system. Here, we're just going to say it's the mass of the satellite. And so that's how they cancel out. And we can just say the accelerations are the accelerations due to gravity. Oops. Yeah. Let's go on to the next one. A car. So this is a rear view of a car turning to the left, and we have a free body diagram in figure 2. In figure 3, they give us this scenario. A car travels with a tangential speed v1 around a curve of radius r and turns to the left, as shown by the rear view of the car in figure 1. A force diagram of the forces exerted on the car with a speed of 5 meters per second as it turns is shown in figure 2. A force diagram of the forces exerted on the car with a speed v as it turns around the same curve of the same radius is shown in figure 3. The speed of v of the car in figure 3 is most likely. Let me zoom out a little bit. Come on, scroll bar. You were just here. This is really annoying. Well, hopefully you guys can see on AP Classroom. Let me end the polling and relaunch polling here. Okay, we have about 3 responses. I think just to kind of keep the ball rolling, we'll go ahead and pause the poll here and go ahead and take a look at it. So if we look at this, the force of friction is 9 times bigger. And we've learned that when we move around in a turn, friction is the centripetal force. So the friction here is going to be mv squared over r. And none of this is changing. It's the same radius, it's the same car, but now, or the same mass, but now the velocity here is going to be the issue. Well, if I get 9 times the force, then the velocity was square root of 9, or 3 times bigger. So because the original velocity was 5, now we're going to be going at 15 meters per second to require 9 times the force there. Oops, let me check the chat real quick. Alrighty, nice. Okay. You got the 3 times, but I had not seen the initial speed. Yeah, okay, nice. So we're recognizing the proportions there. Very good. Yeah, especially as I zoomed out, it got a little harder to see. So whenever you do these like substitutions of just a number, remember that that's the factor. And so maybe we're like, well, what the heck? I didn't get a 3 here. Ah, yes, that's it. What it means is that it went up by a factor of 3. Okay, let's go to the next. Takes you just a little longer to solve. So usually do an initial guess on the whole gotcha. Okay. Oh my God. What happened here? Okay. So for some reason, did it do this with all my? Okay. Let's see here. Can I move this down? Okay. All right. For a moment, I thought it had merged all my images, and then we wouldn't be able to see it. I was going to have to do a separate screen share. Okay. So we have some kind of force probe on a mass, and it reads. Oh, that could be why, because I had the pen selected instead of the select tool. A student places a block on a disk, and the edge of the disk makes 1 revolution at a constant time interval delta t. A force probe is attached to the block and the center of the disk as shown above. So that's this part right here. In an experiment, the student measures the centripetal force exerted on the block when placed at various distances from the center of the disk, while the tangential speed of the edge of the disk remains constant. Which of the following graphs shows the centripetal force exerted on the block as a function of its distance from the center of the disk? So it sounds to me like we're going to keep we have to be careful with their wording here because this could be a gotcha. The tangential speed of the edge of the disk remains constant. Okay. I think I'm picking up what they're putting down. Let's go ahead and do a poll. Okay, we'll go ahead and I'll call it here. So we're going to be changing the distance from the center of the block. So R is definitely changing. So let's go ahead and see what that tells us. Well, the centripetal force, which is the net force, is going to be mv squared over r. And so we're thinking, okay, well, the radius is increasing, so the overall fraction will decrease. Now that would be true if at each of these distances, the velocity of this object remained the same. But the wording here is a little tricky because what I want us to recognize is that as we move around from the edge or from the center of a circle, our tangential speed increases. So not only is the radius of our path increasing, or changing, sorry, and I'm trying to get these arrows in proportion to each other, but it's not working out. But in these instances, these velocities are also going to be changing because what they tell us is that the velocity of the edge remains constant. So what does that tell us? Well, we have learned that V is given by R omega. So if this is constant and I'm always on the edge, that's constant. So what that tells us is that the angular velocity, the thing that this thing rotates at, the rate at which this thing is rotating is constant. So let's go ahead and make a substitution for this. V squared is going to be R squared omega squared. And what we find out is that the centripetal force here is going to be given by m R squared omega squared over R. And what we find out is that it is going to be given by mr omega squared. And this is constant, and this is constant. So it's going to be linearly increasing. So what we find out is that the centripetal force here is going to be answer choice A. And it's because of the way they tell it to us. The tangential speed here at the edge is constant. Yeah, I was going to say, I don't know if you guys can hear my sounds. Let me mute the server for a second. I'm assuming something just came in. Let me just mute the server. Okay. Oh, it's because the other one, the esports, the competition place. Let me just mute that for another hour. Okay. All right. So that's the big gotcha in this one. The actual velocity is changing as we move across, because this thing, while it's spinning at a constant angular velocity, as we move outward, we're going to be moving faster as we move out. So what we do is we recognize, well, okay, this scenario, yeah, you got to go, no worries. Have a good one. Well, if you guys need to go, that's totally fine. I'm going to continue recording this anyways. We still have about 10 more questions. So I do apologize. I do feel like I am moving a little bit slower today. But let me know if you guys had questions over that previous one, because it feels like a big old gotcha. But the trick here is that this is rotating at a constant angular velocity. Not that each of these velocities stays the same as we move out. Okay. So planet X is at a position A, and it reads, oh, I didn't even copy the question. So I'll give you guys the question. So planet X is going to move from position A to position B, and they want us to choose which of these best represents the graph of the tangential speed as this planet goes around in a circle at a uniform rate, or in a uniform motion. So let's see here what we think. And let me see how the College Board actually posed the question. Is in a stable circular orbit around a star. Okay. So we'll go ahead and end the polling here. And so we have to be careful. They're talking about speed. Speed is the magnitude of velocity. Magnitude of velocity. Which means just the fastness. We're not going to worry about the directions. Okay, thank you. I really appreciate that. Horizontal position from A to B if the planet is moving in a counterclockwise direction. So what does this mean? If it's moving around in a stable orbit, that means that it doesn't get any faster. It doesn't get any slower. However fast it was moving, that's how fast it's going to keep moving over time. So we could say that the angular velocity of this is constant. And because it's a circle, the radius is also constant. And so the speed is going to stay constant. And so C is going to be our best answer choice here. And again, let me know if we have questions over that. Now, if we were looking at a plot of the velocity, be very careful. It would not look like either of these. If we actually plotted the velocity as a vector, it would look like a sinusoid. And then because our velocity is directed like downward, if you will, it would start out like this, and it would look like a negative cosine graph, to be specific. So really important, the velocity is a sinusoid, not a semicircle. These guys are semicircles. Okay, no problem. Enjoy your dinner. Let's go on to the next one. Question 14. One end of a string is attached to a ball. with the other end held by a student such that the ball is swung in a horizontal circular path of radius r at a constant tangential speed. At a later time, the tension force exerted on the ball remains constant, but the length of the string is decreased to 1/4 the radius. What is the new tangential speed of the ball? Let's see what we're thinking here. About 6 more seconds. All right. So we'll go ahead and end the polling and let's go ahead and take a look here. So in this case, the force is going to remain the constant. It's the same ball, so the mass also stays constant. We don't need to worry about that. V squared over R squared. So what's going to happen? Well, this is going to get decreased by 4. So this goes down by a factor of 4, which causes R squared to go down by a factor of 16. Let me make sure here. What is the new tangential? The tension of the ball stays the same. Okay. Alrighty. Okay. Yeah. I was like, for a moment, I was like, the velocity can't be. What the heck am I doing? I'm squaring the R. I'm sorry. I am probably starting to get tired. That is a really bad mistake. So it's V squared over R, and R is going to go down by 4. Well, if the force is going to remain constant, that means that V squared also has to go down by a factor of 4. Let me make sure that makes sense. Because this would make a tighter path, which would require more force. So I need to slow my roll so that I don't break the string. So then V squared is going to have to go down by a factor of 4. So then it's going to have to go down by a factor of 2 once we square root it. So it's going to be half the original speed. C is our best answer choice. Most of us were thinking 4 times, but hopefully we remember that square proportionality. One way we can think about it is V squared is proportional to R squared, because if we're doing proportionalities, that doesn't matter because it's constant. Why can you use V equals R omega? The reason why we can't do that here, and we kind of could, M R omega squared. The problem here is that it doesn't really change anything. Oh, sorry. No. It actually changes everything. Well, not that it changes everything, but the reason for this is we're talking about the tangential speed, not the angular velocity. Because the tangential speed is going to depend on the radius and the angular velocity changing.
How come when you make it omega, the formula changes to r omega?
That's only for constant angular velocities. So like that's the big substitution, is we can only do that if we spin with a constant rate. But this tangential speed is going to depend on the spin and the distance. And because the spin will change because the velocity changes, we don't really want to go that route. We could try doing that, but we start getting like, let's see here, equals constant. So we could say R is proportional to 1 over omega squared. And then R is going to be, let's see here, omega is V over R squared. So that becomes 1 divided by V squared R squared. And so we start to get R is proportional to 1 over V squared. R squared goes to the top because the bottom of the bottom goes to the top. So then we can say V squared R is proportional to R squared. That guy cancels, and we still kind of get the same relationship as before. V squared is proportional to r. So you can do that. It's just you're going to make a lot of like substitutions, and you can do the algebra. But the thing is, they're asking about the tangential speed, not omega. So at the end, you have to go ahead and swap the substitution for v equals r omega. Say omega is v over r. So omega squared is v squared over r squared. So this substitution is usually best when something is already spinning at a constant velocity. Even if it doesn't, you can make that substitution, but it gets a little messy. As we saw here, we have to do some bottom of the bottoms going to the top, and then we move this guy over to this side, and then we cancel out one factor of r, but we still get the same expression, which was
Okay,
this
thank
part.
you.
Mhm. All right, let's go to number 15. And so let's see here. We have a board and a block. Oh, let me go back to the click and maybe that'll fix the cursor issue. Not quite. Okay. So let's do this. Okay, so a long, let me zoom out a little bit, and then, yeah. A long wooden board is at rest on a horizontal surface, and there is negligible friction between the board and the surface. A block is sliding along the board, and there is friction between the block. Okay, so there is no friction here, but there is friction here. Rough. And there is friction between the board and the block. At the instant shown in the figure, the block is moving, but the board is still at rest. What happens to the board and the block after the instant shown, and what reasoning supports this claim? So for whatever reason, at this instant, the board was at rest, but the block was moving that way. Oops, relaunch polling. This is pretty cool. If you guys ever go to like the air hockey at like Peter Piper or something, get a piece of paper and then put like a block on it or a puck, and then try to push the top guy, see what happens. Okay, so I think basically the friction is going to tug on this guy. So as the block moves this way, the board would want to see a slide of this guy moving that way and the board moving that way, but the friction is going to bring it with it. And so the board is going to start moving in the same direction as the block, and the block will slow down because the board exerts a force on the block and the block exerts a force on the board. This is Newton's third law there. Number 16. A student must test the maximum force exerted on an object attached to a string before the string breaks. The student ties the object of mass MO to one end of the string and uses the other end of the string to spin the object at a constant speed so that the object travels in a horizontal circular path as shown in figure 1. Figure 2 shows the horizontal force exerted on the object at a time t original. And that's in a second trial, what should the student do to increase the tension in the string while keeping all other quantities constant? Select 2 answers. No, it doesn't. Oh shoot, I did the multiple. Okay. Okay, we'll go ahead and call it here. And so let's go ahead and take a look here. So we could increase the tension, and we recognize that the tension here is the centripetal force mv squared over r. So if I increase the mass, that'll increase the tension. Okay, so I think A is a good answer choice. If we increase the length of the string, what that means is the radius of the path is increasing. If this increases, the tension would decrease. So I don't think we want to increase the radius here. It would be an easier path to maintain. The tighter you make your turn, the harder it is to maintain that spin or that turn. And so you're more likely to slip off the road or break the string. Decrease the time required for one rotation. Well, as time goes down, V tangential, which is given by like delta x over delta t, well, if that goes down, that makes this entire fraction go up. So this is going to go up. So I think the velocity will increase here. And then decreasing the height above the floor is not going to do anything. Very good. Okay. Let's go to number 17. We're almost there. We're in the home stretch. So we have a top view, and it says a block is at rest on a disk that spins about its center as shown. A student must determine the centripetal acceleration of the block when the block spins with a disk as a result of the force of static friction. What measuring devices, when used together, can be used to determine the centripetal acceleration of the block? We're going to select two answer choices. Ugh. All right. So we're looking to be able to measure the velocity and the radius. That's what the centripetal acceleration depends on. V squared over r is the centripetal acceleration. Let me change the pen there. So if we can get a meter stick, we can get the radius. And if we know the radius, we can do 2 pi r to get the circumference. And then if we take the circumference and divide it by the time, that'll give us the velocity along that path, or the tangential speed. So I think the meter stick and the stopwatch are best answers. The reason why the motion detector doesn't work is the motion detector needs line of sight. And so as this turn, I'm sorry, go ahead.
What's line of sight?
So like, for instance, let's say it basically just means that it can only detect things in front of it. So let's say I decide to put my motion detector here. It's only ever going to be able to get the motion when it's in front of it here. So maybe we could get the velocity as it goes here, but there's no way for it to actually give us the velocities throughout the, or like the actual size of the path. So here, if we were really clever with a motion sensor and a stopwatch, we could make it work. But the College Board is saying that the meter stick and the stopwatch works best because you can get the circumference and the time, and that'll give you a good measurement for the velocity. The motion detector will only be able to give you an average velocity in this instant at best. But again, motion detectors only detect motion when things are moving away from them or towards them, because it's using sonar. So all you're really going to get is that I had some object in front of me for some amount of time. So that's not going to work very well. If I put my motion detector here, I don't know, whatever, it's a box, it can detect the ball of the block moving away from it, and you'll be able to get a velocity, but it's not going to be very good. So I think you could still make it work with a motion detector. You just would have to get very clever. And to them, their idea is the meter stick and the stopwatch will do it. The motion sensor will usually also have a time measurement, So with a motion sensor and a meter stick, I think you could get clever enough to make it work, but you would need to explain something along the lines of, well, I measure with a meter stick the radius of the path, and then I use a motion detector aligned tangent to the path so I can get the velocity as it's moving tangently along that path. And then you could go ahead and get it. So I kind of think you could use a motion sensor and a meter stick, but their answer is meter stick and stopwatch. And it's only because a motion sensor can only detect things in front of it. But I think if you set it up so that it's in front while it's moving tangent to the path, you could get that tangent velocity. Let me check the chat. Can we assume that give anything other than the average velocity like acceleration? Do you mean the motion sensor? And if so, the motion sensor can give you displacements over time, and it will calculate velocities over time. And then it can calculate those change in velocities over time to give you accelerations. So motion detectors can give you all of those quantities, but it will usually be calculating the velocity and the acceleration. If you have an accelerometer, and that's standard laboratory equipment, you can just get the acceleration from the accelerometer right away. Okay, here's the Earth and a satellite. A satellite orbits Earth in a circular path at a constant tangential speed as shown in the figure. Which of the following correctly represents the directions of the net force, acceleration, and the tangential velocity of the satellite as shown in the figure? So the satellite is going to be at the bottom of this orbit. In which direction are the net force, acceleration, and the velocity? I chose B and C, but is A incorrect because you can get the mass with time and the radius? Because they want the acceleration, you actually don't need the mass there. And so you don't really need a force either. You just need to get like V and R. Let's see here. Yeah, so yeah, okay, makes sense. All righty, so we'll go ahead and end the polling here. And so if we look at this, we need a force pointing towards the center for the centripetal force, and that will be our net force, F net. An object accelerates in the direction of a net force, so the acceleration is also in that direction. And tangentially, the velocity could either be this way or that way, but I'm going to assume that A is our best answer choice. Let's see here. Yeah, not these guys. Okay. Here's a block with a string attached to it, and that string is going to pass through a little tube, and it's going to have a mass at the other end. A square block is attached to a string of negligible mass and moves in a horizontal circle at constant speed. The string passes through a vertical tube, and its other end is attached to a cylinder as shown in the figure. Which of the following claims can be made by relating one of Newton's laws of motion to an object that travels in uniform circular motion? Okay, we'll go ahead and call it in 3, 2, 1. So Newton's laws of motion say that a force is only, Newton's second law specifically says that objects basically have, unless it's gravity, objects must be in contact with one another to exert a force on each other. So really important, the block does not exert a force on the cylinder. What's going to happen is the string comes in contact with the cylinder, but the block itself is not doing anything to the cylinder. So B is out of the question. Cylinder exerts a contact force on the block. By that virtue, again, the cylinder itself is not making contact with the block. There's a contact between the string and the cylinder, and that effect is transferred along the string. It's what keeps it kind of like, keeps it as the pivot point. And then D, the forces exerted on the string are negligible. Not true. They are significant. It's just that they cancel out. And so A is our best answer here. The block exerts a force on the string. Because this object wants to shoot away, it pulls on the string and the string pulls on the block, creating that tension. If I were to draw a free body diagram of the string, there would be like the centrifugal force from the block pulling it away, its tendency to move out, really just the tension. And then we would have another tension pulling the string that way, and we would have some kind of contact force from the two. And this tension, these two tensions would probably be the same, but we'll just call them T1 and T2. All right, let's go to the next one. 20. We're almost there, guys. We have position versus time squared. An object falls towards the earth after it is released from rest as a result of Earth's gravitational force. A student uses a motion detector to create the graph of the object's displacement as a function of time squared, in which the object is in free fall. How can the student use the graph to determine the acceleration AY of the object while it is in free fall? So let's go ahead and relaunch the polling. Let's zoom in. And this is only one correct, so I'll just choose. Scroll bar, you are really annoying me today. I've never had this issue, or like at least not in one of my review sessions. Okay. We'll go ahead and end the poll here. And we know that, for instance, like delta y or delta x is the original velocity in the direction. So I'm using y, 1/2 times time plus 1/2 the acceleration in that direction times time squared. And it's released from rest. Question, or are we good? All right. So when we plot this versus time squared, this behaves like our horizontal x. This behaves as our vertical axis y. And we get y equals mx plus b, where the slope here is going to be 1/2 the acceleration. So we say 1/2 ay is really m, or ay is 2m. So use the slope of the graph and set it equal to 1/2 ay to solve for ay. So B is our best answer choice. So it's not the slope in this case, it's the 1/2 of the acceleration is the slope. So just kind of be careful with that. You want to look at everything in front of that part, and all of that is the product of all that is your slope. So you said,
wait, Mr. Gus, that's half the slope because that's like the proportionality.
Ooh. Not so much the proportionality, but here the slope is equivalent to 1/2 the acceleration. The proportionality, I would say, is t squared to y, or y is proportional to t squared. And the constant of proportionality is the m, and the constant of proportionality in this bigger equation is 1/2 ay. I don't know if that answered your question there, Anthony.
Yeah, it did.
Okay. Right. 21. Two satellites orbit a planet of mass m as shown above. Satellite A has a mass of 2m in a circular orbit of radius r, and satellite B has a mass of m and travels in a circular orbit of radius 2r. Each satellite travels at a constant tangential speed. How does the gravitational force on A from the planet compared to the gravitational force on B from the planet? Sorry, I got the hiccups. I always get the hiccups. Like, I need to stop drinking like energy drinks before these. Or eating for that matter. I had some chips earlier. I get home hungry. I'm gonna go have dinner after this. Ooh, I wonder what I should eat. Alrighty. So in this case, I don't think we can make the argument that they have the same orbital speed or the same tangential speed. All we know is that it is constant, and the reason for that is because it is in a circular orbit. If this were elliptical, Kepler's laws would tell us that the further away we are, the slower we are, and the closer we are, the faster. So if we do our fancy math, we find out that V orbital is going to be given by square root of g mass of the planet over r. So really important, the mass of the satellite actually does not factor into the speed necessary to maintain orbit. If I took a an object that is much bigger than another little object, both of these need the same velocity. So if we look at this, more than anything in this scenario, it's going to depend on r. And so the closer satellite will be A. And so I think FGA is going to be larger than FGB. Ooh, I don't like this reasoning. Because satellite A is twice as large as satellite B and is half the distance to the planet as satellite B. I think that's the better part. I don't think this part really matters. Give me 1 second. Let me make sure that I'm in agreement with the powers that be. Oh no, they signed me out. Oh well, I will be the powers that be. Let me know if we have questions over that. Let's look at the other ones just in case. Was to travel at a greater. Oh, sorry. I'm answering the wrong different question. We're talking about forces. Okay, so then let's see here. The force due to gravity is the centripetal force, and that's going to be m. Sorry. Big mass of the planet, mass of the satellite, all over the distance squared. And so here, even though we pick up twice the mass for one of the satellites, this guy has twice the mass. This becomes mass of the planet times 2m all over radius r, which gives us essentially 2m planet m over r squared. This is the force due to gravity on A. The force due to gravity on B is going to be the mass of the planet, and this guy's going to have a mass of m, but it's going to be 2r quantity squared away. So what we find out is that this is mass of the planet times the mass of the satellite all over 4r squared. So even though it, and so yeah, you used the wrong formula, but you got the right answer. I forgot that this was, yeah, no. I fumbled. I was answering the wrong question. We want to look at the force due to gravity. You could kind of reason it and say, okay, well, the velocity is going to be here, and then we can combine that with v squared over r. This guy is going to be g mass of the planet all over r over r. R's get squared, and we get basically the same thing as before for the centripetal acceleration. And so even if we kind of messed up the mass part, recognizing that 2 times the distance gave us 1/4 the value, we should expect this guy to feel a larger gravitational force. Another way to think about it is as we get further away from a planet, the gravitational force is going to get weaker by the square. So that's another way to think about it. So here, because it was twice the distance, this guy needed to be 1/4 the mass to get the same amount of force as that satellite B would experience. Okay, last question, and then we're here on the home stretch. An object starts at rest and moves in a horizontal circle such that its tangential speed increases linearly as a function of time. Which of the following graphs shows how the centripetal acceleration behaves as a function of time? Okay, we'll go ahead and end the polling right about now. Okay. So if we look at this, the centripetal acceleration is proportional to v squared. Now the velocity is going to be increasing. So, or the tangential speed is going to be increasing. So because it's moving faster and faster and faster, we need a larger acceleration to change our velocity's direction. So we should have something that is changing when increasing. Now, because it's proportional to v squared, even though the tangential speed increases linearly, the acceleration increases linearly squared. So that, or not linearly squared, that's bad wording, but it's going to change by the rate of this guy's change, which is linear, quantity squared. So I think C is our best answer choice. If they said that this increased quadratically with time, like if the velocity itself had an acceleration that was also increasing, and that acceleration was linearly increasing, so if speed increases quadratically, then the acceleration, the centripetal acceleration would be increasing by v squared squared, which would be v to the fourth. And so that bad boy would be like, cool, something like that. Okay, so I think that's it for today. Thank you for stopping by. Hopefully this made sense. If you have any questions, let me know. I do aim to meet at 10 tomorrow for the free response of this unit.